Okay, so good morning, and so this will be the last lecture on the Ising model. Okay, and so far we have uh, seen only beautiful last lecture on the Ising model, but so far we only done an approximate solution. Okay, and I have told you that there are some issues. So what we're going to do today is solve the 1D Ising model exactly. Okay, and so one dimension is a line, and so 1, 2, so on and so forth up to there are n sides. Okay, and the Hamiltonian is just this sigma minus v times okay, and our setup so far has been sigma I takes values plus or minus half. Okay, so we have a finite chain with n sides where the spins are located. Okay, but so the point here is that we need to specify boundary conditions. Okay, okay, for an open chain. Okay, so for instance, example would be say that sigma 1 equal to sigma n equal to plus half. Okay, and the rest are allowed to fluctuate. Okay, this is one example of an open boundary condition. There could be many more. Okay, or we could have sigma 1 equal to minus sigma n equal to half. These are opposite these things. Or it could be random. We could put some random probabilistic stuff, but this is sort of simpler. Okay, so this is one thing, but we can also consider periodic boundary conditions. BC is for boundary conditions. Okay, but periodic, what it means is that you sort of put another link, if you wish, which will connect these guys. So sigma, there's one more link which will connect sigma 1 and sigma n. Is that clear? What a periodic boundary condition is. So we'll have two things: open boundary conditions, where you give some, you tell me what sigma 1 is and what sigma n is. The other one where it is periodic, then there's nothing to specify. Okay, so these are the two kinds of boundary conditions, and we would like to compute the partition function. So I'll pause here. Are there any questions?
So if you put periodic boundary conditions, essentially closed chain, right?
It's a closed chain. Yeah, absolutely. Okay, so this is now a closed chain. Thank you. Okay, so we need to compute. Okay, and okay, so that's what we want to do. So what is that? Z is sum over all configurations. So we can just write it like this: sigma 1 equal to plus or minus half sigma n equal to, so there are n summations. Okay, so this is what we have to do. So there are 2 power n configurations. Okay, so we would like to do this sum, and so the question is, how do you go about doing this? And so the method we're going to use is quite famous. It's called the transfer matrix method. Okay, so we'll introduce a matrix V, okay, such that with index structure, it's a 2 by 2 matrix, so something like the sigma I plus 1 kind of thing, such that Z okay. So this is the Z sigma 1 sigma n is a partition function where we specify sigma 1 at one boundary and sigma n at the other boundary. Okay, that's what we will do, such that sigma n is just V power n. You take this matrix V, multiply n copies of it, and look at it, sigma 1 sigma n complement. Is this clear? So I'm just saying what I'm not telling you what V is, but we will write it in a moment. And Z, periodic boundary conditions, is you get basically trace. Okay, so this is what you will get. I don't know if this is V power n or V power n minus 1. It doesn't matter. Okay, so check this. Check if this is what this has to be. Okay, later you can do this. Okay, and then so this is the claim. Okay, so and V is just some, V is a 2 by 2 matrix, symmetric matrix. Okay, so now let us construct this V. Okay, so is the idea clear? Okay, so also we would like to take the thermodynamic limit. Okay, and okay, so in this case it's just saying that it's take n to infinity. Okay, so that's what we want to do. So is the strategy clear? So I have to construct for you this V matrix. Okay, so the idea here is the following. So just some notation from quantum mechanics. Okay, so hopefully you know this. So let's say there is some quantum state sigma I, which could be the ith guy taking plus 1 and minus 1, or plus half minus half. Okay, so equal to identity operator in the 2 by 2 Hilbert space. Does this make sense to you people, this notation?
Yes, sir. It is projection operator, right?
Yeah, so this, yeah, without the summation, it's a projection operator onto the ith spin. Absolutely. So there are two projections, so it's the sum of those two projection operators. Yeah, absolutely. Okay. So what we do is the following. So let's just so this is what we have in mind. Okay. And so what we so this is the picture I have. Of course, we have to sum over all i's, sigma i's. Okay, so you can see that so these guys, if I sum over I plus 1, it will give you identity, and so that's how you can keep eliminating things. Okay, so the idea here is let's consider this. Okay, and let's choose a basis where so this guy, there will be four terms, has four possibilities. Okay, and I read this as follows. It's just the contribution to e power minus beta h when the from the inter. So we'll also I'll put first b equal to 0, but later I'll show you how to put it back. Okay, so what we would like is that so b equal to 0 for now. Okay, so I'll just write a matrix and write this is plus minus, this is plus minus. Okay, so let's say that the sigma I is the row label and sigma I plus 1 is the column label. Okay, so if you're here, so an h then is just minus j summation sigma I sigma j. So we have to compute. So I just want to identify with e power minus beta h. This is what we want to identify. Okay, so what should I put here? And h is just when b is 0, this is it. So sigma I plus 1, right? So this is what we have. We focus on that particular term. All other terms don't contribute. So I'll call this hi or whatever. So we'll focus on this term. So what should I write here? Right? Does this make sense?
Yes, sir.
Okay. Similarly, this guy will also be the same. Both are. What will be off diagonal when they are opposite?
Minus beta j.
That's all. This is the B matrix with then B is 0. Okay. So now you can see. Okay. So now easy to see. Okay, at least periodic. Now let's first. Let's do the sigma 1, sigma n. Okay, so now I want to just take the case of 3, 1, 2, and 3. So each bond will give us, so this will give v square. Okay, so this will be v power n minus 1. Okay, this is what I was saying, I wasn't sure. So it is n minus 1. I fix that, right? And the last two are not specified, so it's just sigma 1. Is this clear? Okay. Now comes the interesting part. What about periodic? Z periodic. We add one more bond. That bond will give us one more V. So that will be just okay, summation over the bond or whatever. So V n minus 1 in okay, sigma 1 sigma n, V of sigma n sigma 1, and you sum over all of them. Okay, but what is this? Right, you row column, you this thing, it's multiplied, it becomes v power n sigma 1 sum over sigma 1 makes it trace. Is this clear? These are our solutions for b equal to 0. Are there any questions, comments?
Yes, sir. Sir, can you at first that sigma I before that this pi summation pi equal to that identity matrix.
Yeah.
Can you just explain a little bit? Can I think about a vector or something like
Yeah,
that?
yeah. So good. Let me just do it. Yeah. So I need to do one sample calculation. Okay. So we will fix on this. We'll fix on the I plus 1th guy. That it can take two values. Okay. So this will be sigma I v sigma I plus 1 sigma I plus 1 v sigma I plus 2. Okay, there are other terms, but we are just focusing on this. So this is equal to, so we just take the sigma I plus 1, this summation, we can take it inside. This is equal to that is a claim. Is this okay? Because now I'm using sigma I plus sum over the two values of this. So V identity V becomes V square. So I'm taking this inside here. I can do that. Is this clear now? What I'm saying?
Yes, sir. Sir, can you just for use that after you have written using that summation of sigma I plus 1
Yeah.
equal to that thing, right?
Yeah.
So can you just give some reading assignment who are not familiar with how this happens?
So there are two ways to go about it. If you have done quantum mechanics, you will know this. So if you are not familiar also, it doesn't matter. It really doesn't matter in the following sense that you can just think of this. Okay. So what I'm saying is there are two ways to understand this. Okay. So this is the quantum mechanics way. Okay. But the easier way to think about this is the following. So think of this as the matrix element. So V is a matrix with the matrix element sigma I sigma I plus 1. That's all. You give me that. So if sigma I is, say, plus and sigma I plus 1 is plus, it will give you the V plus plus entry, so on and so forth. That's what I did first. Okay. So then, so the same summation can be written like this. V sigma I plus 1. That is this guy. The next guy, you don't need to learn quantum mechanics for this. So these are matrices with some matrix elements of the matrix written this way. So this is like column of this, row of this. This is exactly matrix multiplication. This is equal to V square. Same thing, same calculation. This is definition. Okay. So the sum over sigma is our carrier. So what is happening is you're thinning down, right? So you do it at the I plus 1th thing, you do it, you're done. Then you go to the ith guy, you do it on the I plus 1, so on and so forth. Each time the power of V will keep increasing till you hit the end where it will be sigma 1 sigma. That's how we got V power n minus 1. This is what my first method was. Okay.
Sir, here you are using two Z, is Z sigma 1 sigma n and Z periodic. What is the difference between them?
Yeah, so what is the difference? Because so this is so here what it says is that here there are let's say sigma 1 can take two values, sigma n can take two values. So there are four possible boundary conditions, and so the V power n minus 1 is also a 2 by 2 matrix. So each entry in the matrix will give you one such partition function. So if I take sigma 1 equal to sigma n equal to plus half, then it's like the upper left corner. Off diagonal will be one being plus and the other being minus. So this is right. It's saying you pick the sigma 1 sigma nth element of this matrix V power n minus 1. That's what this says. Okay.
And Z periodic is for whole matrix.
Yeah. So Z periodics. Yeah. Z periodic. We have to do two things. Okay. Which is we have to add, we are adding a bond, right? This was the picture I had. Where is the picture here? So there will be one more V which will come from in plus 1, in I1, which I put it here separately. But we have to sum over sigma n, etc. So that just becomes trace, standard definition of trace. So for periodic, we'll get only one partition function. For the case of open, we'll get four possible boundary conditions. And so there are four. So there are five partition functions I've written in this way.
Okay, sir.
So the easy method, you don't need quantum mechanics. Okay. So now so the point is we want to add the magnetic field. Okay, so this is not so clean, the argument, but it will work. Okay, so what it says is that, so we had okay, so here you add a piece which would be what you would get. So you just want to add eta or e power beta b by 2. Let me put that in yellow. Okay, so you add this diagonal piece and little bit of thought. Okay, or a calculation will show that this works. Okay, so first the point here is that the B term in the Hamiltonian is just depends on the spin at one side, but the diagonal pieces are contributions when the neighboring side also has the same thing. So you just kind of say that we associate, just yeah. So maybe I'll draw a picture that might help me also. So what we have is something like this, right? So what we have is that, so let's say this is sigma I plus 1, sigma I plus 2. Okay, so it's like this term here will be, the energy or whatever will be minus B times sigma I plus 1. Here it will be. So the whole idea here is that you would like to shift it to the edge. So you'll get here sigma I. So what you do is half of this you bring here, other half you bring here. You share like this. Okay, this kind of way you do. And so you write it as sigma I plus 1 kind of thing by 2 kind of thing you can do. And up to some constants it will work. Okay, so you can check that this picture will tell you that it works. Okay, so what I'm saying is write this like this. So in the periodic case it will work. So what we have is minus B times I. Okay, sigma I, which we can write as minus half B into a half I put already outside. This is what I'm saying. Okay, at least for periodic there are no issues. This works. Okay. Check. I mean, for it probably I think it works even for the other case. Okay, is this clear what I'm saying? What I do is I just modify it by putting this. Okay, that's all. So what this says is that if they are opposite, you get 0. So sigma I plus 1, if one is plus and one is minus, that gives 0. So that doesn't contribute. Okay, so that's how this is a way to understand this. Okay, so now we are kind of done. So Z periodic. Okay, is okay. So what we do now, so there is so V is a 2 by 2 matrix. Okay, it's a symmetric matrix. That means it's normal, so it can be diagonalized. Okay, it has 2 eigenvalues. You don't even need the eigenvectors actually. 2 eigenvalues, lambda 1, lambda 2. Okay, so question to you is, what is Z period? Yeah. Hopefully you know this formula, right? Trace of any matrix is the sum of its elements. And if you diagonalize it also under similarity transformation, so it will just be this. Is this clear?
Yes, sir.
Okay. So we need to compute. So once we compute, so strategy is okay. And let assume that lambda 1, and it's symmetric, so it has real eigenvalues. And let lambda 1 be greater than lambda 2. Okay, so then in the limit, n tending to infinity, what we get is that periodic. So I'll keep writing p only now, it's getting too long. And write it like this: lambda 1 power n. Okay, so this, so what is lambda 2 by lambda 1? It is less than 1, right? So in the thermodynamic or the n tending to infinity, what happens to this?
Do lambda 1 to the power n.
Yeah. So the lambda 2 by lambda 1 is very less than 1, and you take as n goes to infinity, that term drops out. So this just becomes approximately, okay, which is good, lambda 1 power n, and which is gets better and better as n tends to infinity. So in the thermodynamic limit, we can say that the partition function is just the dominant eigenvalue. Okay, so let's now, so that means we are now, we have to determine the eigenvalues. Okay, so what is it we do usually? Determinant of v minus lambda I should be 0. Okay, so that's what we will get, or lambda I minus v, doesn't matter whichever way we do. So we'll get minus lambda whole square minus the product of this beta j by 2 equal to 0. Okay, so what we get is e power beta j by 4 plus beta b by 2. Okay, so these will be the solutions. So lambda will be this is correct.
Yes, sir.
It's not correct. Right? I mean, magnetic field, if it is plus, it will give one sign, and minus, it will give the other sign. The rest of so this term is not correct. Very simple. So now, now you have to expand it, etc. So I won't waste my time. So I'll just write the answer. So the solution is lambda 1 and 2 are the following. You can check whatever I'm writing. So this is inside the square root. Okay, this term is what we get. Okay, so the plus sign is a greater sign. Okay. So now now that we have got this thing, we can compute f. It will be minus kbt log of z periodic, f periodic. That would be minus nkbt okay, times log zp, which would be log of lambda. Now we can compute. Of course, lambda 1 is this complicated function which is here. Okay, which is given here, and but we can just write that thing. So then magnetization. What is magnetization? It is just e power is equal to df by db. Okay, so that would be 1 by n. We have to remove the for one magnetic thing, so that would be by b. So that would be minus kbt by lambda 1 d lambda 1 by db. Okay, so exercise. Simplify, take the derivative and simplify it. Simplify the expression for n for the average magnetization per side to get m equal to okay. So you get something like this. Hopefully there are no mistakes earlier. But now we just, in another 2 minutes, we'll just study what happens to this. Okay. So first point here is that what happens. So first thing is when b equal to 0, okay, and 0 and beta not equal to infinity, beta finite. Okay. When b equal to 0 and beta finite, what can we say? What happens to m?
0.
Okay. So what it says is that for any finite beta, we have 0. We have m equal to 0. In other words, implies we have a paramagnetic phase. Okay. Of course, strictly as okay, but as t tends to 0, of course, we expect t tends to 0. It's some limits you have to take. Okay, and then if you take b goes to say 0 plus or b goes to 0 minus from the negative side, m show that m will become all aligned upstairs, so it will become half Okay, so this is sure. Take this to show this. Okay, this is not hard actually. So at t equal to 0, it goes to the ground state. But if you had b is 0 plus, then it will prefer the plus n. If it is 0 minus, so you do this limits. You first take beta to infinity or whatever. Okay, so then so when you take beta to infinity, you'll see this term will go away, and you will see that. Okay, is this, there is some half missing. I think there's a half. Okay, so okay, so I'll stop here. So what? So you can see that. So the statement is that in d equal to 1, there is really no phase transition, if you wish, at finite temperature. This is a proof. Okay, so I will just in another 2 minutes I will tell you what happens. The d equal to 2 Ising model. Okay, this was solved by Onzager, and there are many other solutions, but the idea. Okay, so what he showed. So let's do periodic. So that periodic now in two directions. Okay, he showed that that can be written as trace of v1 v2 power n. Okay, so or is it v1 power? So he had a product of. Now I'm trying to remember. Is it like this? Yeah. So he had two transfer matrices. I want to warn you, that might be imprecise what I'm writing here, or even wrong. But the basic idea is what two transfer matrices, to a set of transfer matrices, which is so the idea. I mean, the you might think, can I consider the 2D lattice as a bunch of chains, 1D chains? Okay, but then the number of bonds are quite a bit, right? If it's a cubical lattice, so it's not so simple. Okay, so how do you do that? So there's some cleverness involved in this whole story, and he has to do this thing. So he put two transfer matrices and was able to. Okay, this was the idea, and was able to compute. And so what we did for the 1D was elementary, but methods are not elementary. And the funny thing is that the kind of methods he uses is very commonly used by people working in particle physics or high energy physics, but not somebody in condensed matter physics. Okay, and so he was able to do this thing, but however, okay, so here there is a phase transition at finite. So there. So this was the key thing. You can go ahead and this thing. However, this method doesn't work if we turn on a magnetic field. Okay, so 2D Ising model with magnetic field. Okay, so there the idea there would be V1, V2, V3. You have three of those guys. Same thing. Okay, doesn't work for 3D Ising model. So, but as McCoy and Wu in their famous book say that the fact that Onzager solved the D equal to 2 model exactly and has given a concrete proof, he says that we don't particularly care for getting exact expression for the 3D or any other Ising model, because we know what we wanted was conceptually that we should show that there is a phase transition at finite t, and that was already this thing. But there are numerical simulations, and people are very, very clever. They actually show that there is a phase transition, etc., etc., etc. Okay, so that sort of concludes what I wanted to say uh, about the Ising model. And so coming next is real gases. And we'll see how real gases actually are. I mean, there's a nice relationship with the Ising model. Okay, especially a beam field will be very, very. We can show how similar they are. Okay, so I'll stop here and pause for questions.